What's up?
I didn't really say what I talked
Yep,
to you about.
I got your email. I just haven't done anything about it yet. I promise you I will. Actually, do me a favor before you leave today, like at the end of class, just remind me, and I'll just go do it. We'll just go together and do it, me and you. We'll go together. That way I won't forget, and that way you'll have peace of mind.
So, you know how like we go to assignments and there's regular chapter 1 and 2 when you try 5 times and
Yep.
once they try 2 times?
Yep.
If you get a lower score on the second try,
It'll count your highest score.
Okay.
Good morning, sir.
Hey, how's it going?
You know I know the second, I think video and the 7 seconds.
Yeah, there's a different link, sorry. Send me an email after class, and I'll send out the other link.
Oh, okay, thank you.
Actually, I'm going to post a better video, too. I have the high-def video with good audio.
Oh, okay.
The streaming video is okay. It's not bad. But the high-def video from the camera and the digital recording from my voice, much better.
But you're saying the same stuff from 2 years ago on YouTube.
Yeah, the classes don't change.
Yeah, so I just watched it now.
Yeah. These videos I think are a little bit better because they're a little clearer.
Yes, it is.
But yeah, it's the same stuff.
Shoot, when I'm listening to it, I'm either sleeping, shaving, or cleaning. So I'm not even watching.
In your head.
Yeah.
I'm still getting 30 frames per second. I'm still happy with that.
So you thinking about pushing the exam back to another Friday, or?
No, next week's good. You don't want to push it back too far. Then they get too much material on one exam.
Wait, so you're, wait, is it still next Friday?
Yes.
Oh, okay, I was like, wait, what?
Did I ask if you want to push it back?
I don't like exams any more than you guys do.
That sounds like a decent idea, you know? It's less.
No, that'd be another week of material you'll have to learn.
That is also true. Have to learn.
I mean, so far it's okay. It's no.
Yeah, it's not like
serious.
crazy stuff.
Yeah.
You know? Like even trying
The perversion thing is just, you know, it's killing the significant.
the significant figures.
Yeah,
Yeah, because sometimes
yes.
I'm like, what I don't like is like the ones that have to be in scientific organization and I don't realize it until later. And I'm like, oh, how did it get 2 significant figures? I was like, scientific figures. Oh, I was gonna say, I'll give you one. I was like, no, I'm not serious. But we can use our phone.
You just sit in there.
Oh, this we can use our phone calculators in class. Yeah, just not on the test. To bring that, no, I usually do like an independent study. If I have some trouble with something, then I'll like go from like, what am I doing? But I study like throughout the week. Not. I don't study throughout. But I start on like Wednesday, Thursday, and start like looking at stuff that we can see. I take 5. But it's not like, they're not like intense classes. It's like, you know, art appreciation. That's not, you know.
Taking the habits.
No, I'm not taking it yet. I didn't want to take like all of the super. There's like, yeah. Taking off the general ed first. And I took chemistry in high school, but I didn't learn. He didn't know what he was doing. He was like, okay guys, like he taught significant figures in one day. So to my chem teacher, he just like 3 weeks. Because he kept getting them off. And he was like, oh, so like there's scientific notation, and then you use that. And you're like, what is scientific notation? And you're like, oh, it's like, you have the number times 10, and we were like, okay. Yeah, I was in sophomore and then he was his only chem teacher, of course, so we didn't know what he was doing. So we had one from our class who taught us all this stuff. So also our valedictorian, so he knew what he was talking about. But it's like, he didn't start doing that until the end of the year. So it's like, we're all sitting here like, I got a B, I guess, I don't know how to get a B. But, so, that's why I'm taking it now, because I'm like, I have to actually learn like chemistry. Yeah, I take it after this class. I take it with me at studio.
Okay, I see that.
Yeah.
Yeah.
Oh, well, there's a reason she had.
I mean, that's good.
Yeah, but it's not okay. It's like, I've been hearing about his labs. It's like, oh, we doing like something serious. I'm like, whoa, this sounds cool. No, we're doing something fun. She's like, she literally told us the first day, oh, we have tests, right? And you have exams. But if you don't feel like taking the exam, that's what you can at home. Reach out to the proctor. And if you need some help from your friends, then ask your friends for help too. And it's not like when they're watching you from book, so open book, open notes, those are medicine.
Okay, thanks.
And she went to our first labs and was like, oh, I don't have all the maths, the maths of the pennies. I need to take, more pennies maths. And she's like, oh, you see, I need a copy from someone else. And you leave the maths of the pennies. But we just do what's on the lab. Understand some things, like how many decimal points to use with the ruler, like analog versus using a digital decimal point, versus using one for volume. But at the same time, it's just like, kind of this gives you, this is what we're going to do. Just do that. You can have her. That's why she has good grading, because she doesn't.
That's why she had. I mean,
that's why it's really funny, because like he'll teach something in the morning, and she'll be like, he'll teach like significant figures. She'll be like, okay, this is how you use significant figures with volume, this is how you use it with rulers, this is how you use that. And he'll be like, I think we're doing something with like mass or energy, and then right into chemistry lab. Oh, you're taking the mass, and then it's just like, I learned it in the morning, and I do it now. Yeah, with her.
because you already know.
Yeah, so he'll teach it in the morning.
So you don't have to worry about it.
The day.
And I see my student, I was like,
Yeah, I tried to look for his chemistry lab class because I saw a couple of bad reviews. I saw a lot of good ones, but some of the bad ones I was like kind of worried. I was like, last week I was like, maybe.
just learn money. I learned so much out of that. Just learn. That's all. There's no way.
That's what I wanted to do. So I was like, if I have the same chemistry teacher and the same chemistry lab teacher, you could ask me it's like a better understanding. And I kind of looked for his class, like he said, well, no seats. Okay. Yeah, okay, what's for you? I'm going to be
All right, guys, 1 minute till we start, so let's get ready for a quiz, please. Piece of paper, pencil, pen. You won't need a calculator today for this quiz. You might be missed today. That's why I write this stuff down. Sometimes I forget. All right, as always, if you want to team up with a friend, you're welcome to. But don't forget, on next week's exam, you are working on your own. So keep that in mind as you do these quizzes, that you're going to be required eventually to do this stuff on your own. So try it on your own first, and then maybe collaborate with someone. Make sense? For the quiz. Yeah, but I recommend you do it on your own first, and then check your answer with a friend. Because on an exam, you're 100% on your own, right?
It would have been nice.
It'd be nice, but that's not realistic, unfortunately. All right, ready? Hey, quiz time. There you go. You have 5 minutes. Talk about it when we're done. About a minute left, guys. All right, guys, there's your time. Let's hand that bad boy to the front, please. There we go. Come on, stop. All right, let's get up there. Don't make me wait for it. Remember, I will take it when I'm waiting. Thank you. Thank you. Thank you. Thank you very much. So, exam next week, yeah?
Yeah.
So you might want to listen to what I'm going to say. So that means you might want to be quiet so I can say it. All right, next week at 9 o'clock, the exam will start. All right, so there'll be no live streaming during the exam because that's just a waste of time. So get here 5 minutes early. So I am going to start on time, and you'll get no extra time if you're late. All right. The exam will be 1 hour and 15 minutes, probably. 50 multiple choice, 5 to 10 free response questions. Free response questions are questions that we kind of do on the board, you know, like work out the math, units, canceling and stuff. I want to warn you, any answer in the short answer section, multiple choice, just answer that on a Scantron, right? Just go buy a Scantron card from the bookstore, answer all the multiple choice on that. If the multiple choice questions are not on the Scantron, I will not grade it. I will not grade paper. I will only grade Scantron, okay? The free response questions have to be on the paper, have to be written out logically so I can see what you're doing. If you give me an answer with no logic, I will give you 0, whether the answer is right or not. Okay? I'm looking for the logic more than I am the answer. All right? So make sure you do all the unit cancellations and all that fun stuff, right? Make sense? Bring a piece of paper, bring a calculator, non-programmable, pen, pencil, eraser, maybe 2 each to make sure you have plenty of writing material, or writing instruments, shall we say. Once the exam starts, you can't look in your bag. So make sure you have enough pens and paper, pens and pencils on your desk. All right? There are no questions during exam, so don't think you're going to be able to ask me anything. If you insist that I talk to you, all I'm going to say to you is answer the question as it appears. That's all I'm going to say. Okay? But please don't even raise your hand. Because what happens is, this guy over here raises his hand, someone over there raises their hand, and everyone's going to raise their hand. And all I'm going to say to all of you is answer the question as it appears. Okay? That's all I'm going to say. So please, just do it. Now, if there's a question that has an issue in your opinion, you think there's an error in the question, the syllabus clearly tells you how to handle it. Write down your concern on the exam. Just make a quick little note describing what you think the problem is. If you're right, you'll get full value for that question. But if you're wrong, if you don't have any answer there, you'll get 0. So make sure you give an answer and express your concern. Does that make sense? Kind of hedge your bets, right? So I have something to grade. The exam will include everything we've covered up to and including today. So everything we do today will be on next week's exam. Well, I shouldn't say will. Maybe on next week's exam. All right? All right, so back to the periodic table and back to atoms. So last week we learned all about this table thing here, groups and periods. What's a group? Right. Groups are the vertical ones. They go up and down. Periods go Left to right or right to left, however you want to look at it. Right, very good. Those are groups and periods. We learned about group 1. Group 1 are called the alkali metals, right?
Yes.
Group 2 are called the alkaline earth metals.
Yes.
Group 3 through 12 are known as transition elements or transition metals. 13 through 16 don't have a cool name. 17 are halogens, and 18 are the noble gases. Sound good? All right. Moving along. Metals, nonmetals, and metalloids. Now our periodic table, this one for example, there's this fancy little bold line. On the periodic table you'll get on the exam, this line is black because I don't print in color because I get in trouble. But every periodic table that you're going to have at your disposal will have this line drawn through it. It's called the zigzag line. I call it the staircase. It looks like a staircase, right? On the left-hand side of that staircase, those are metals. On the right-hand side of that staircase, those are non-metals. And above the staircase, those are metalloids. Below the staircase, those are metalloids. Now, aluminum, you got to be careful with these little rules you make up, right? Aluminum right here, you would think it's a metalloid, right? But it's not. It's metal. Ooh, that's weird. Come back to that. Also, if you look at the left-hand side of the table, everything over here is a metal. But wait a minute. Hydrogen is also here. Hydrogen is not a metal. Hydrogen is a gas. Hydrogen is actually a non-metal. Why is it here? It's a great question. I'm sure some of you are asking yourself, well, why did they put it over here? Is this to confuse students? No! We don't try to confuse students. It's here for a reason. And we'll get to the reason later on, probably today. But just accept the fact that hydrogen is a gas, so it should be it's a non-metal, but it's here for other reasons. Okay? Make sense? Alright. So, that's how it works. To the left of the staircase, metals except hydrogen. To the right of the staircase, they're non-metals. Above and below the staircase, except for aluminum, those are metalloids. Metals. Here are some properties you should know. Metals are shiny and ductile. They're also called malleable. All that means is you can pound it out to flat sheets, you can bend it, you can twist it, you can do all kinds of stuff with metal. Think for yourself. At your house right now, I guarantee most of you, if not all of you, have metal cookware. Most of you, if not all of you, have something that's made of aluminum for cookware. A pot, frying pan, or something like that. That's aluminum, right? You've also seen aluminum foil, right? Made by Reynolds usually. Got your sandwiches or something. That aluminum that makes Reynolds wrap is the same aluminum that makes the pot you're cooking your spaghetti in. It's the same aluminum. But the aluminum foil, you all will agree, is much thinner. Right? Aluminum pots are much thicker. So that tells us something about a metal. You can roll it out nice, pound it up nice and flat, really thin, or you can shape it into something thicker. Your wiring in your home is made of copper metal. An electrician can pull wire through really cramped spaces because the metal can actually twist and turn, right? And still stay together. It's a property of metal. Metals are also good conductors of heat and electricity. Think about your frying pans at home. They're all made of metal. Yes, you can get ceramic ones, yes, you can get glass ones, but most of the time they're made of metal. Either aluminum, cast iron, or stainless steel is usually what they're made from. Okay, these are metals because they can conduct heat very well. Put a frying pan on the stove tonight. Be careful. Do this. Put your hand down in there. As soon as you turn the burner on, put your hand on down there. You can feel the heat coming through the frying pan almost immediately. That's how fast metals can conduct heat. Electricity. Your copper wiring again. It's made of copper, which is a metal, which can conduct electricity. All metals conduct electricity, some better than others. Non-metals are dull and brittle, and they are poor conductors. Now, a non-metal, let's look at the periodic table. Non-metals are out here. Carbon is the best example, the simplest example of non-metal. If you have a pencil, pens don't work, but pencil, if you have a pencil, look at what they call the lead of a pencil. Okay? The lead of a pencil is not made of lead. Lead is actually a metal. Lead is down here. This is lead. This is metal on the left-hand side of the staircase. Pencil leads are made of carbon. It's called graphite, but it's actually just pure carbon. Now, if I asked you to take a hammer to the pencil lead, would that pencil lead shatter? Absolutely it would. Because non-metals are brittle. They break easy. Now, if you look at your pencil lead, you agree that it doesn't have a shine. It doesn't shine like silver would, or it doesn't shine like gold does, right? It's very dull luster. Non-metals are like that. They're poor conductors, and they're what they call good insulators. Now, let's think about the wiring in your home. For anyone who's ever pulled wire, you know it's surrounded by plastic, right? It's surrounded with plastic. The main ingredient, the main element in plastic, guess what it is? Carbon. It's the main ingredient in plastic. Now, it looks nothing like graphite, I get that, but it's made of carbon and hydrogen. Both of them are non-metal. Both of them are poor conductors of electricity, right? That's why they coat them. If you can now handle electrical wire and not be attacked, because they have a good insulator. Now, metalloids are kind of hybrids between metals and non-metals. As you go from metals into non-metals, these things start behaving both ways. For example, have you ever seen purified silicon? Silicon's right here on the old periodic table. So it's a metalloid. Silicon is actually quite shiny, has quite a nice luster to it. Not quite as good as, say, a metal would have, but it definitely has a shine. And it's brittle. You hit it with a hammer, it'll shatter. So it has some properties of both. And in fact, metalloids are not great conductors of electricity, but not bad conductors. They can conduct electricity. So they're known as semiconductors. Now you may have heard that term semiconductor before, because most computers are built with that. Well, I think all computers are built with that. Semiconducting metal, or not metalloid. All right? How's that? Pretty good? How's that? Pretty good? All right. Study check. Identify each of the following as a metal, a non-metal, or a metalloid. Let's go over here to the table. Sodium. Sodium is way over here. What is that? Metal or non-metal? Or a metalloid? It's a what? Metal. Very good. Chlorine is over here. What's chlorine? A what? Non-metal. Very good. Silicon is right here. Metalloid. Nice. Iron. Metal. Very good. And carbon. Our good friend carbon right there. You can't yawn when you talk about carbon. Try that again. So non-metal. No yawning when you talk about carbon. All the other elements you can yawn all you want. But carbon is the base element of life, and that should be exciting to all of us. Okay, the atom. The atom. Let's write the title down, please. The atom. The wondrous world from which we're made from. The atom. It's an amazing, amazing thing. If you ask me. The atom. The atom. All right. Little history lesson. I'm not going to try to get too deep into the history of the atom, but it is somewhat interesting. Back in the day, there was this guy named Charles Dalton, and he had this theory of, atoms, basically, kind of follows this. He said that, okay, atoms are these tiny particles of matter, and that's absolutely true, still true today. Small, little, tiny things. Elements are similar to each other and different from those of other elements. Okay, that makes sense. That's kind of weird to say. But back in the day, when he started talking about this, that was easy, that was new. Right? Basically, what he's saying is atoms of carbon are not the same as atoms of nitrogen. They're different. Wow, groundbreaking at the time. Now, these atoms can rearrange themselves to form new chemicals. Whoa! That's a big deal, right? We take that for granted today. Yeah, that's how it works. But back when these guys were thinking about this, that was new, that was novel. Wow, that's a great idea. Right? So that's dull. Now, without getting too deep into the history. Oh, one thing at the bottom. Sorry, I missed this point. Pardon me. This part right here. Atoms never created nor are they destroyed. That's an important concept. In normal chemical reactions, atoms are not created, they're not destroyed. They're transformed, they're changed around, but they're not. The atoms themselves don't change. Okay? All right. Now, inside of the atom, there are three different charged particles. Well, two of them are charged, one of them is not. There are these things called protons. And protons have a positive charge. P for proton, P for positive. Protons are positively charged. Then there's also these things called electrons. The electrons are negative. We have protons, we have electrons. Protons are positive, electrons are negative. And guess what? They attract each other. They attract one another. So if you have an electron and a proton, they will attract. It's like two opposite poles of a magnet will attract each other. However, with the positives together, and they actually repel each other. With the negatives together, and they repel each other. There's also these things called neutrons, and neutrons are neutral. N for neutron, N for neutral. Neutral meaning no charge. It's not positive, nor is it negative. It is neutral. Not bad, right? You've all heard this before, I'm sure. So it's old hat to you. That's good, right? All right, let's talk about J.J. Thomson for a minute. Now, you don't ever have to memorize these guys' names. That's not important. But I do want you to have a feeling for what they used to believe and how we kind of transform science. Basically, these theories were really good. People thought these theories were true until they didn't. And how did they figure out they were not true? By experimentation. Remember that? First day, hypothesis, all that stuff? Might be on next week's exam. All right, Thomson realized these things called cathode rays have a negative charge. Whoa, negative charge. That's pretty neat. Negative charge, okay. These cathode rays that have a negative charge, he's called electron. He discovered the electron. Okay? Now, once he discovered the electron, they knew about protons. He knew about protons. He discovered electrons. Now the question is, all right, we know the atom has protons, we know it has electrons. Where are they? In terms of the atom, where are they located? Right? Now you gotta remember these guys are English. I'm pretty sure Thomson was English. He might have been Scottish. And back then, they didn't have all the cool little tools we have now to examine these things. You had to kind of wonder, where are the electrons in relationship to the proton? And he came up with, I think, a pretty cool idea. Wrong, but a cool idea. He said that the atom will resemble plum pudding. Now, you have to understand, for English people, Europeans, pudding is not like Jell-O pudding. That's more of a mousse. Pudding is like bread with fruit in it, right? Those of you who are like Commonwealth people, you've had pudding before, probably. So now, Thomson thought that the atom was like a plum pudding, where the bread of the pudding was the positive proton, and the electrons were like raisins stuck in the pudding, or plums stuck in the pudding. Okay? That's what he thought. And it's a great idea. It's wrong. It's a great idea. But remember, use the data you have to make a hypothesis, right? And you test the hypothesis. Does that make sense? All right? So now, Thomson's theory stuck around for a while. People liked it. It worked until it didn't. And then this other guy, Rutherford, he came along. And he did what is considered by many to be the most important experiment in our lifetime. At least in my opinion, one of the most important experiments ever done. He devised an experiment to find the proton. To find it, to see what he could deduce about the structure of the proton and electron. What did he do? He took some gold. I'm not joking when I say this. This is all real. He really did this. And he did this back when there were no computers or TV. I'm not sure about radio. There might have been radio. He took gold. Seriously, gold. Rolled it out real thin. Wafer thin. Probably, I think, what I've read is 3 or 4 atoms thick. You could still see it. Like you could see it, you could touch it. It was real. You with me? You have to understand it was real. If you could see it. It's right there in front of your eyes. Okay? And he took this gold and he shot positively charged particles at it. He had a way of making these things called alpha particles. Okay? He shot these alpha particles at this gold film, this gold foil, this thin layer of gold. You can see
With your naked eye, you can see this gold. You can see it right there. Okay. Now imagine, if you would, I had a way of shooting arrows at that wall. And let's imagine the wall was thin, like a piece of paper. You know, these walls are quite thick, but imagine they were thin, like paper, right? If I shot 100 arrows at that wall, it would make one hell of a hole, wouldn't it? It's a pretty big hole, right? And that's logical, right? It's logical. The arrows have mass, take up space. The wall has mass, takes up space. When they collide, they have to either embed into each other or tear apart, right? And we all know if you shoot arrows at that wall, the wall will have many holes in it, right? So now, let me just show you. Let me just show you a picture. When this guy took his little positive charge source, shooting a beam of positive charge here, this purple thing here, that's simply a fluorescent screen. All it does is when one of these particles from here hit this screen, it flashes light. That's all it does, just flashes light. Okay? So you can see, whenever a particle from here hits somewhere on here, you can see where. Okay? So now, here's our gold. It's definitely there. You can see it, touch it. Here comes some particles, and guess what? Almost all of them go right through it without making a hole. Whoa, right? Think about that for a minute. They all go through it without leaving a hole behind. The gold, at the end of the experiment, the gold is completely fine. You can use it over and over again. Completely fine. So all of these particles, now you have to understand, these particles have mass. They occupy space. The mass is easily measured. Gold atoms have mass and occupy space. He shot particles at that gold film, and most of them went directly through it. It's like me shooting arrows at that wall, and the arrows going through the wall without leaving a hole. It's impossible, right? But at the atomic level, it's not impossible. When things are small enough, you can do it. Now, what did this tell us? Well, first of all, it indicates to us that matter atoms are mostly empty. Now, let's see what that says. These particles went right through that gold without leaving a hole. That means they must have found an empty space to travel through, right? Must have. There's no other way to do it. If they hit another atom, say for example, one of these little particles hits the gold membrane, finds an atom, and bounces off at a weird angle, right? You know, some of them actually bounce off at strange angles. A few of them, not many, but a few of them ricochet. Okay, wait a minute now. If the particle hit something and ricocheted, what it hit must be pretty massive, right? It hit it. And it's like shooting a bullet at that wall and the bullet bouncing off. Why? Matter hit matter and it ricocheted. Right? So this leads us to something very, very important and groundbreaking and astronomically important. Atoms have a central core where most of the matter is located. Atoms have a central core where most of the matter is located. So think about all the matter that's in an atom. Protons, electrons, and neutrons. All three of them are in there. Most of the matter, most of the mass, most of it is in this central point. Are you with me so far? And that central point is called what? The nucleus. Very good. An atom consists of a nucleus, and that nucleus is known to contain the proton and the neutron, and that's it. The nucleus contains the protons and the neutrons. Now, where are the electrons? The electrons occupy the space around the nucleus. They occupy the space around the nucleus. They are not in the nucleus, they're around it, somewhere. The nucleus. Now, the nucleus has the protons and the neutrons. That's pretty much all of the matter of an atom is there. The electrons do have some mass and some volume, but the protons and neutrons have most of it. So the atom is mostly empty. The electrons are around the nucleus somewhere, Protons and neutrons are in the nucleus. And that's what those little particles are bouncing off of. Every now and then they hit one and bounce off. Pretty neat, huh? Pretty neat. Now you may be asking yourself, why is this so important? Because this discovery led to countless other discoveries that we're still discovering today about how atoms work. And if you understand how atoms work, you can understand how life works. Because life is built on molecules, right? Or compounds. So if you understand how the atom works, you can understand how life works, you can understand how diseases work, you can find cures for diseases. Now, obviously it's a very long extension from this, over 100 years of study, but it all started here by understanding the base nature of the atom. It's extraordinarily important to understand that. All right, atomic mass unit. Forget this top statement. I don't ever test you on that. All I want you to know from here is the proton has a mass of about 1 AMU, and AMU is an atomic mass unit. So, a proton has about 1 atomic mass unit. They are slightly, actually, heavy. They're actually 1.007, but you could say it's 1. It's rather than 1. The neutron also has a mass of about 1 atomic mass unit. It's actually a little bit heavier than the proton, a little bit more massive than the proton. Okay? All right, so I've already told you that most of the mass in an atom is in the nucleus. The protons and the neutrons are in the nucleus, and their mass, atomic mass unit, is about 1 each. So now, you go down to electrons, and electrons are very small. Look at their mass. Compared to these masses, this is extraordinarily small. Not non-existent, just small. Is that okay? Most of the mass of the atom is in the nucleus. That's where the protons and neutrons are. The electrons are somewhere around the nucleus, and they're very small. Not too shabby, right? How are we doing? Good? You all asleep yet? You guys look draggy today. Is everyone draggy? You don't need to stand up or something? All right, go ahead. Come on. This poor girl's like, yeah, I want to stand up. There's no one standing up with her. Come on, be nice. Stand up. Get up. The next time we have to do this, we do jumping jacks. 50. That'll wake you up. All right, stretch out there a little bit. Ah, there we go. Yeah. Only a half hour to a 3-hour class. Actually, only 33 minutes. Yeah. But another hour till break time. All right, so that's atomic mass unit. Study check. Which of the following subatomic particles fit each of the descriptions below? The subatomic particles are the protons, neutrons, and the electrons. They are found outside the nucleus.
Electron.
Very good. They have a positive charge.
Proton.
Where are they found?
In the nucleus.
Very good. They have a mass but no charge. And where are they found? Very good. See, it's not hard, right? Pretty simple stuff. Remember, at one time, this was all extraordinarily hard. Because this is all discovered. Very interesting stuff. Write down the title, please. Atomic number and mass number. Atomic number and mass number. You just stood up. I feel you. I made a classic mistake last night. I fallen asleep on the couch at 6, waking up at 10, up till 4. Lying in bed going, this is going to be really hard in the morning. It's like a lot of coffee. I feel pretty good right now. We're on 11 on the track. All right. Who here has ever heard of atomic number? Good, very good. Atomic number. First things first. The atomic number is a whole number. The whole number. Specific for each element. each element has its own atomic number. And it's a whole number. So let's go over here real quick. See these numbers right here? Those are not whole numbers, are they? They're not atomic numbers. Are you with me? Okay, good. Now, the atomic number is the same for all atoms of an element. The atomic number is the same for all atoms of an element. And here's the kicker. The atomic number is equal to the number of protons in an atom. That's the kicker. That's the most important thing. Every atom of a specific element will have that number of protons. Let's go to the periodic table. I love carbon. Carbon has an atomic number of 6. It's printed right there. Now, every periodic table is slightly different. Some tables put it to the top right, some put it above, some put it over to the left. Usually they're on top. Almost always they're on top of the little cube, the little square. Here, atomic number 6. Boron, atomic number 5. Nitrogen is atomic number 7. Okay? This is no problem. So that means that carbon has 6 protons. Nitrogen has louder. Boron has 5. Now, what if I had an atom of carbon with 6 protons, and I magically, through some kind of witchcraft, gave it 7? It becomes nitrogen. It actually changes the element, doesn't it? Okay? By changing the protons, you change the element. Okay? So, an element or an atom with 6 protons must be carbon. There's nothing else it can be. An atom with 29 protons is always copper. There's nothing else it can be. Okay? The atomic number makes the element, makes the atom. 6 protons, carbon. 10 protons, neon. 17 is chlorine. Let's get crazy. 23 is vanadium. That's not too crazy. 74. See that W down there? What's that stand for, do you think?
I'll let that one marinate for a minute. W. Not the hotel. It's tungsten. Don't ask. Don't know. That's weird, huh? Protons. All right. Atomic number is the number of protons in an atom. Just write the title and the title volume. The other stuff's just reiterating it. Atomic number equals protons in the atom. Just write the title. Just write it. Big, bold, tight, circle it, underline it, double exclamation points, both sides. It's important. I'm making a big deal out of this. It's really important. All you gotta do is look at the periodic table and you'll know how many protons are in an element or in an atom of a specific element. Atomic number equals the number of protons. And the protons are found where? Louder! Okay, everybody!
In the nucleus.
Well, that wasn't everybody, but you got louder, so that's okay. Atoms are neutral. Write that down. Underline it. Double underline it. Exclamation points on both sides. Maybe a happy smiley face. Just draw your attention to that. That's an important point. Atoms are neutral. Which means the positive charges equal the negative charges. That's what it means. There's no other way to be neutral. To be neutral, your positives must equal your negatives. Therefore, the number of protons equal the number of electrons in an atom. ATOM. In an atom, they are equal. Protons equal electrons. So, if we go over to the periodic table and I say, how many protons does sulfur have?
16.
How many?
16.
How many electrons?
16.
How many electrons does aluminum have?
13.
How many electrons does chromium have? Gold, cadmium, silver, palladium. Easy peasy, right? They all have the same number of protons and electrons because they're all atoms. Careful, not everything's an atom. Eventually we're going to get into these things called ions. And ions, this is not true. In atoms, this is true. Ions, it's not. We're going to get there probably today. All right. Oh, a study check. Let's do it. You want to yell it out? Are you going to yell if I let you yell? You got to let it go. How many protons does nitrogen have?
7.
How many?
7.
What's the atomic number?
7.
How many electrons?
7.
Zinc. Zn. How many protons?
30.
How many electrons?
30.
What's the atomic number?
30.
Pretty easy, right?
Yeah.
Sulfur.
16.
And
16.
And
16.
very good. They're all the same number. Mass number. This is where things change. Write down the word mass number, or the phrase, sorry. Mass number. Mass number. Let's start here. Everybody, read this. Out loud.
It's always a whole number.
What?
It's always a whole number.
Now say this. Say mass number is always a whole number.
Mass number is always a whole number.
Are these whole numbers?
Yeah.
No, they're not. Right? They're not whole numbers. These numbers that are written here on the bottom of the element, those are not mass numbers. So please don't confuse them with that. Okay? Mass numbers are always whole numbers. The numbers that are written here are not whole numbers. We have decimal points. Okay? These are not mass numbers. In fact, mass numbers are never, ever printed on the periodic table. Never. There's never going to be a mass number on any periodic table that you're going to see. But we can define it. A mass number equals the number of protons plus the number of neutrons. Essentially, the mass number is telling me how many particles are in the nucleus. That's what it's telling me, because that's where the protons and the neutrons are, right? Right? This is telling me how many particles are in the nucleus. Now, I want to just... That's the abbreviation for number, right? That's hashtag, I get it, but like back when I was young, with pterodactyls flew and stuff. No, not even a joke? Okay, wow. Yeah, make me feel old. That's good, right? The week before an exam, make me feel old. Good job. Make that question a little harder. So that's number. So I'm going to start using that as my number because I don't want to write number out anymore. So, mass number of protons plus the number of neutrons. That's what mass number is. Are you with me on that? And that's all that it is. It's nothing special. Now, this is a formula that I will not give you on your exam. You have to know this. You have to know the definition, okay? Mass number is number of protons plus the number of neutrons. It's a very simple formula. Okay, let's talk about this question. We'll do it together. An atom of lead has a mass number of 207. Yeah, it's big, right? Yeah, that's pretty heavy. 11, oh, mass number 207. Okay, so it's lead, right? Pb. You find it on the old periodic table. It's right down here. What's the atomic number?
82.
How many protons does it have?
82.
Write that down. Lead. Pb. And the mass number 207. Protons. Protons are abbreviated P. Equals 82. How do we know that? It's the atomic number. Now let's skip over neutrons. Let's go down to C. Electrons. How many electrons does it have? It has 82, right? Electrons are abbreviated E. But you can guess what neutrons are abbreviated to? N. Exactly. We're not very creative up here. All right, so the protons are 82, the electrons are 82. We get that from the periodic table. Easy. B. Neutrons is a little bit more involved. Well, we know that the mass number is equal to the number of protons plus the number of neutrons, right? So we know this. We know this. Can we rearrange for that?
Yes.
No problem, right? So the number of neutrons equals the mass number minus the number of protons. So it's 207 minus 82. Which works out to be? Very good. The number of neutrons is 125. How was that, guys? Yeah. I would, yeah. I would definitely show me something that you knew how to do the problem. You just didn't, like, I'm not accusing you of anything, but like, a lot of times students will write down the answer. Yep. You gotta show me something. You can't just leave it blank and be like, ta-da. You gotta show me some kind of indication that tells me that you logically this is the problem. If you just do the formula and then this, I would be okay with that. Something. You know what I mean? How was that, guys? You guys all right with that? Let's do one more before we get into electron. What if we had, I don't know, nickel 60? So nickel, Ni, with a mass number of 60. How many protons, electrons, and neutrons would there be? Go ahead and work that out on your own. How many protons does nickel have? How do you know that? The atomic number on the periodic table, right? How many electrons? How do you know that? All atoms are neutral, so they have to equal, right? Neutrons a little tougher, huh? So mass number equals the number of protons plus the number of neutrons. So the number of neutrons then equals the mass number minus the number of protons. So then you plug the numbers in, right? 60 minus 28, and you get 30. Then that would be 32. We got it right. Nice. It's not hard, right? All right. Electrons. Electrons. You notice that protons and neutrons basically kind of threw them together and kind of went, yeah, they're the nucleus. And then electrons get their own thing. Kind of tells us the importance of an electron. And when I tell you this, it's, one would say it's actually very true, but chapter 5 deviates a little bit. Chapter 5 is nuclear chemistry, And that's a little bit different, a little bit of an exception to all the rules. Most chemistry, normal chemistry, electrons do everything. Protons and neutrons are there, they have to be there, but the electrons do all the work. Okay? So electrons are the most important thing to learn about in chemistry. They explain everything. It's important that we understand at least at a rudimentary level. Now, electrons are very, very complicated. They're complicated. Let's say it that way. It's a very, very easy way of saying they're complicated. It's really hard to understand electrons because they don't make a lot of sense. We guess they do, but then they don't. See what I'm saying? They're weird. Electrons are weird. All right. Let's jump through a lot of this stuff. Yeah, I don't want to do any of this. This is all very hard stuff. First thing I want to talk about though with electrons. I don't want to talk about too much of what's called quantum mechanics, because that starts to get really, really, really crazy, really, really fast. What I do want to talk about, and I would encourage you to go look up on YouTube and watch some of these really cool animations they have, is look up wave nature of an electron. Wave nature of an electron. Look up constructive and destructive interference and all that kind of stuff. Electrons get really complicated really fast. If you really want to know what Schrodinger's cat, another crazy idea. Look up quantum entanglement, spooky accidental distance, all this stuff. It's called going down the rabbit hole. Once you start, you won't stop. Because it's really interesting. It's fascinating how electrons work. It's fascinating how much you know. It's fascinating how much you don't know about how they work. Now there's spooky action of this, that'll lead there. Spooky action out of this. Einstein coined that phrase back before he died. Spooky action of this. Now don't watch the lectures from Harvard or anything like that, because those will be way above your head. Watch some of the animations they have, some of the low-level stuff that's really kind of interesting for you. It's really complicated. Your mind will explode. Your head will go, oh. And then you'll be like, wow, this is another one. It's really cool. It's really interesting. All right, what do you need to understand at a rudimentary level about electrons and about how atoms work? Atoms, protons, neutrons in the core, right? They're in the nucleus. The electrons are somewhere out there. Somewhere out there. Here's a fun fact. We don't know where. We know where they should be, but we don't know if they're there. And what we have are called probability maps. You know where they should be. But are they there? Maybe. Maybe not. But we do know one thing. If they're going to be here, they're going to be here, right in this energy level. And if they're not here, they're going to be in this energy level right here. They won't be in between. They're not going to be here, they're going to be out here somewhere. They won't be in between. They're going to be either here, or here, or here, or here, or here, but they won't be in between. They just can't be. They just will not be in between. That's one of the weird things about electrons, right? They magically disappear and then reappear. Whoa! Yep, that's how they work. They magically reappear, disappear, reappear, disappear. And when they do that, believe it or not, they give off light. That's weird. They give off light when they do that. Wow. Electrons are interesting. But what I want you to understand is that the energy of electrons is quantized, which means it's either here, or it's here, or it's here, or it's here. But it's not in between. It's like books on a bookshelf. You can't put a book in between these energy levels, can you? You just can't. It won't exist there. It can exist here or here. Okay? Now, that's important. That's an important idea. Let's talk about electrons. We know every atom has a nucleus, right? So just draw a dot. That's going to be our nucleus. That's where the protons live. That's where the electrons live. And now, somewhere outside of there are the electrons. And remember, electrons are quantized, so they're either here, or they're here, or they're here, but they're never between. Never between. Okay? So that means that there's an energy maximum out here, energy level. If you want to think about it in terms of cute little things you can remember, let's call the nucleus the beach. And let's call this little circle I drew a street. So this is A1A. This is the beach. This is the best seat in town. It's the closest to the nucleus. Are you with me so far? So that's where the electrons are going to want to be to start with. They're always going to start there. Why? It's closest to the beach, where the big money lives. Now, just like A1A is limited space, this street has limited space. So inside of here somewhere, there are 2 electrons maximum. In chemistry, we call this a shell. And this is called the 1 shell. The 1 shell is the closest shell to the nucleus. It is the closest street to the nucleus. It is the lowest energy, because it's the closest to the nucleus. Remember, these are negatively charged, right? And there's the positive charges. These things want to be close to that. In this, there are 2 electrons max. So the first shell, the first quantum of energy, can only have 2 electrons. It can have 0, it can have 1, and it can have 2, but it cannot have 3 or more. Only 0, 1, or 2. 2 is the max. So the first energy level, somewhere in here, are electrons, we think. Probability is they're in there. They don't have to be. Whoa. It's interesting, because we don't know where they are. You want to see another cool video? Look up Heisenberg's uncertainty principle. It's not part of this course. It's part of 1045. All right, so now we're going to build another street in our little electron town. Another energy level, if you will. Now this is a bigger street. So imagine you've gone from A1A to Federal Highway. Bigger street, more room. Hold more electrons. Hold more people. This is called the 2 shell. Somewhere in there are the electrons. Somewhere. Somewhere. Don't worry about where. Somewhere. Maximum 8. Maximum 8. You can have 0, 1 through 8, but you cannot have 9. Never. Never, ever, ever have 9. So the first shell, 2 people can live there, 2 electrons, maximum. The second shell, 8 maximum. So far, we have how many electrons? 2 plus 8 is 10. You with me so far? So now, if the street is full, no one else can live there, what do you do if you're a city manager? You make another street. The street will be bigger. This is another energy level. So you just jump out to another energy level. Now this is called the 3 shell. Now, the 3 shells where things get interesting. In fact, we're not going to talk a lot about the 3rd shell. I'm going to tell you a few things about it. The 3rd shell, well, this time. Eight electrons is okay, but it can hold 18. But 8 is okay. 8 is actually good. Certain elements will only, well, sorry, I shouldn't say it like that. Certain elements are completely fine with 8, but you can make them take 18. Okay? Now, I want you to remember 8. For every question but one on your exam, there might be a multiple choice question. Hint, hint. Well, the answer is 18. Right? I know, right? Gotta get your attention. Right? The question will be something like, what is the maximum number of electrons in the third shell? And you will not say 8. You will say 18, because that is the theoretical, well, that's the actual maximum. It can hold 18. Are you with me on that? Okay. And we'll stop at the third shell, because there's actually 7. They get bigger and bigger and bigger. In fact, the 7th shell holds 32 electrons. Yep. That's a great question. Yes. Depending. Depending. Yeah, you can think of it. Yeah, you can say that. Yeah. Yep. We're going to do it different. We're going to think about that in a different way. But yeah, what you're saying is true. But don't think about 18. Think about 8. Only for that one question is it 18. Okay. Because it's true. It is 18. It is 18. I don't want to lie to you. Now, I'm not going to draw 18 dots there, but you get the idea, right? That's how electrons arrange themselves. So far, so good? Now, some of you may have heard in other chemistry classes about these things called orbitals, S and P and D and all that. That's not part of this course. You're welcome. It's made your day, I guess. Wow. And orbitals are cool. Well, come on, they're neat, but we don't talk about them in this class. All we care about are the numbers. 2, 8, 8, sometimes 18. Maximum 18, but usually 288. Got it? 288. Say it again. 288. All right, but 18 is the max, right? Yes. So that one question, 18 is the answer. Because that's true. It is 18. It can hold 18, no problem. All right, so now we've learned all of this. We can learn something incredibly important about the atom. Electron arrangements. Where did the electrons go? There we go. I want to do this question with you. I jumped over all the explanation of how to do it, so I'm going to do these questions with you. I think doing them is easier than describing it. Write the electron arrangements for each of the following. Basically, this question wants to know how many electrons are on each energy level. That's all it wants to know. So I'll go to carbon. I say, okay, carbon. How many number of 6? How many electrons do you have? Okay, 6, right? So I'm going to arrange those 6 electrons like this. Carbon, 6 electrons. E negative is how you abbreviate electrons. There's another way to abbreviate. So, how many maximum on the first shell? 2. So write 2, comma. If I have 6 electrons and I find 2 at home, how many do I have left? 4. How many maximum on the second shell? So 4 can easily fit there, right? Does that make sense? So the arrangement of the electrons in carbon are 2 on the first shell, 4 on the second shell. Oh, we'll say on in first shell. Okay, that's what that is saying. 2, 4. 2 on the first shell, 4 in the first shell, 4 in the second one. Is that okay with everybody? That's pretty easy, right? It's not supposed to be hard. Okay, now silicon. Ooh, a little bit different. Let's try this one. You don't see that blue in the back? How many electrons does silicon have? 14. Wow. Okay, well, we got to start from the first shell. How many on the first shell? 2. How many maximum on the second shell? How many is that so far? How many do we have left? 2, 8, 4. Or how the electrons are arranged in that atom. 2 on the first, 8 on the second, 4 in the third. See how that worked? You had to build out from the center. Because remember, all the electrons want to be close to the nucleus, right? They want to be close to the nucleus. Now, a good question that a lot of people think about but never ask. Why is it 2? Why isn't it 20? If they all want to be close to the nucleus, why can't we put 20 here? Great question, right? Why can't we just cram them in there, right? Remember, electrons repel each other, right? Right? Let's imagine you're the nucleus, and you guys are electrons, right? So I'm attracted to there, but you guys are also attracted to there, right? And guess what? I don't like you guys. You don't like me. right? So I try to get closer to the nucleus, and you guys say not so fast, and you repel me backwards, right? You push me back. That's why I have to jump up to the next energy level. That's why it's quantized. But anywhere in between here and there, the energy is too much. I have to get out of it. So I come back further, right? Now, this is not part of this course, but it's kind of fun to think about. I am an electron. They are electrons. They're not thinking or feeling anything. They're just reacting to energy. Okay? It's possible for me to disappear from this shell and reappear in this one. And then guess what happens? I kick one of them out. Right? How do you know? And remember, we're all electrons. You can't tell us apart. How do you know? Right? Isn't that cool? I think that's neat. Anyway, what's next? Oxygen. Atomic number. How many electrons in oxygen? 8. So it's going to be what? 6. Very good. Who's the last one? Nitrogen. How many electrons? 7. What's the number? How's everyone doing with that? Is that okay? Yeah. Yes.
Why isn't it like one? Like, what's the oxygen? Why isn't it one?
Right. Good question. You always max out yourself. So you always fill the first one, then go to the second one, fill that one, then go to the third one, fill that one, then you go to the fourth one and fill that one. Yeah, you have to remember these are all just probabilities. But there's a 95% chance that it's here, there's a 5% chance that it's not. You know, and that's just how electrons work. Like, there's no, like, someone really famous, I think it was used before, don't remember what it was before, said if you want to know what the electrons are, you have to consider the entire universe. They're out there somewhere. But we don't really have to know where they are, we have to know where they should be. That's probably where they are. And they behave them. So far, away. Good question. That's not one. So what if I wanted you to write the electron arrangement for hydrogen, where there's only one electron? What would it be? Just be 1, right? So number 1. Okay. What if it was helium? He. That's right, 2, right? What if it were lithium? Be what? 2, 1, right? 2, 2, 2, 3, and so on. So that's how it works. You guys okay with that? All right, very good. Now I know that seems silly, right? This kind of seems silly. It seems easy. Chemistry's supposed to be hard, right? Right? Yeah, it's supposed to be hard, right? We're going to come back to this phenomenon, and it's going to be clear why we do it, but we have to kind of finish off this chapter. Write down the title, please. Trends in periodic properties. Trends in periodic properties. Okay. Trends in periodic properties. Group number and valence electrons. Whoa, wait, what? Valence electrons? That's a new term, isn't it? You might want to write that down. Valence electrons are the number of electrons in the outermost energy level. Oh. Number of electrons in the outermost energy level. Underline that. Circle it. Put a star beside it. Happy face. That's incredibly important. And the group number gives us the number of valence electrons for the representative elements. For the representative elements, right? For the non-transition metals. All right, let's take a look at, you know what? Let's do lithium. 3 electrons, right? 2, 1. Let's do sodium. Sodium's 11, right? 2, 8, 1. And potassium. Okay. 2, 8, 8, 1. Now, lithium, sodium, potassium, and then the rubidium, cesium, and franklinum are all in group 1, aren't they? Everybody agree they're all in group 1? So, according to this, the group number gives the number of valence electrons. So according to this, lithium, sodium, potassium should all have 1 valence electron. Valence electrons are the outermost electrons. Are you with me? So, if you look at lithium, this is the first energy level, this is the second one. So this is the outermost one, it's the one that's furthest away from the protons. Are you with me? So this is the valence electron. That's the valence shell, is the outermost energy level. The valence electrons are the electrons that are in that shell. So do you agree that it's 1? Do you agree that here it's also 1, isn't it? Here it's also 1, isn't it? Everybody agree with that? So all group 1 elements have 1 valence electron. The valence electrons are the electrons that are furthest away from the proton. They're in the outermost shell. They're the street that's furthest away from the beam. And they are extraordinarily important. They are extraordinarily important. All right, let's do boron and aluminum. Boron has how many electrons? 5. So boron will be 2, 3. What about aluminum? 2, 8, 3. And we'll stop there. Now, this is where you have to be a little bit careful. Because the group number here is 13, right? So all you got to do here is ignore the 1. So the 1 is not there. So what's the number that's left? 3. So boron and aluminum should have 3 valence electrons. How's that work? Is that okay with you? Let's do a couple more. Let's go further out. Let's go to oxygen and sulfur. Oxygen, 8, thank you. That's 2, 6. Sulfur, 16, thank you. 2, 8, 6. Oxygen and sulfur are both in group 16, right? So if you ignore the 1, you have 6, right? So 6 valence electrons, and in fact it does, right? Y'all see that? Now, do the electron arrangement for fluorine. Fluorine has 9, and do it for chlorine. Chlorine has 17. You do it. Do the electron arrangement for fluorine and chlorine, and then tell me how many valence electrons you end up with, and does it match the group number? Oh, 7. Ignore that 1. It's 7. Chlorine. F and Cl. Do the electron arrangement real quick. It should correspond to the group number if you ignore the 1. Electron arrangements, they're fun, right? They're easy. It doesn't be one of these things. Yeah. Yep. Yep. No. 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 It's 8. So, in order to explain why you don't put 18 in the third shell, you actually. All right, you ask. All right. Oh, that's a good question. I want to test on it. If you look at the first period, how many squares are on the first period? 2, right? How many electrons maximum in the first shell? 2. That's not a coincidence, right? If you were to draw the electron arrangement for hydrogen and helium, it would be 1 and 2. Right? So the squares correspond to electrons. Are you with me? If you go to the second period, how many squares are there in the second period? Oh no, second period was all the way across the right. 2, 4, 6, 8, right? How many electrons maximum on the third period? Third shell. Second shell. 8. Count this. Third. 1, 2, 8, right? That's where 8 comes from. The third shell can have 8. But, and also, the third shell, I'm not lying when I tell you, the third shell, first shell goes across, the second shell goes across, the third shell goes across, but it can also go down. So these metals here are actually using their third shell. How many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 18 comes from. And now here's something really weird and wild, right? I'll just tell you what it is. Go write this down. If I was to do the electron arrangement for rubidium, you guys don't have to do this. I've never asked you this. It would be 2, 8, 18, 2, 8, 18, 8, 2. You asked. You asked. It's always 8, except for that one part. Okay? The metals do funny things. There's a whole field of chemistry called inorganic chemistry that deals with the funny things metals will do. Transition metals especially do funny things. Interesting, but not what we want to learn about in this class because it's far too difficult to understand. But a great question nonetheless. All right, so what's the electron arrangement of fluorine? 2, 7, right? So it's 9 electrons. What's the electron arrangement of chlorine?
7.
What group number is chlorine in? So if you ignore the 1, how many electrons should it have? 7. Very nice. So the valence electrons are 7. So, if I come over here to the old periodic table and I say, how many valence electrons does hydrogen have? How many valence electrons does cesium have? How many does barium have? How many does beryllium have? What about, you can't do this for the transition metals, boron, aluminum, gallium, indium, thallium, lead, tin, uranium, silicon. I'm just trying to refresh my knowledge. How about neon? 8. Chlorine, selenium, lithium. Wow. Right. The group number tells you how many valence electrons there are. Now, yeah. The transition metal, 3 to 12.
Yes.
You asked to look back to the 18 electrons. Right? So the valence shell, if you want to talk about this valence shell, right? Valence shells are the outermost shells, right? So here, this is period 3, right? This is period 3. This is also part of the period. This is also part of the third shell. So these electrons are in the third shell, so are the electrons that are down here. This is level 4, right? Someone said 2 iron, okay. So iron would be 2, 8, 2, 6, 7, 8. Be 2, 8, 8, 2 would be iron. I told you it's weird. I'm never going to ask you to do the work. I'm never going to ask you to do anything beyond argon. Well, they gave you calcium, but probably not. Okay? After calcium, you start getting into the transition metals and things that you use strength. I mean, it's interesting, but it's beyond the scope. 1045 is not the same. And then, if you want to take advanced inorganic, you can do it on a lot of different stuff. It's just not something that, you don't have the background in this class to talk about. So I don't want to confuse you. What is it? All right. Now, noble gases, yeah?
Yeah.
We talked before how they were pretty much chemically inert, right? Didn't we talk about that? Yeah, they don't react with anything. They're chemically kind of cool. They're chill, right? But group 17 are reactive. They're highly reactive. Group 16, they're reactive. Group 15, reactive. Everything's reactive. Over here, group 1, reactive. Group 2, reactive. Reactive. Everything's reactive. All All these elements react, except for these. Now, I'll just tell you the truth. You can make them react. If you treat them the right way, they will react. If they don't like to react, they'll do it. They'll explode usually after you make them react. So there's something special about them. They're extraordinarily special because they don't react. Now you have to think back in the day, people were discovering elements and discovering how chemistry works. Everything reacts, right? So you know something's going on. It reacted. It changed colors, it blew up, it made fire, it did something, right? And then these inert things come along and they don't react with anything. That's peculiar. Something special about it. Let's do the electron arrangement of helium. It'll just be simply 2, right? Let's do neon. 2, 8, right? Let's do argon. So 18, right? 2, 8, 8. If we were to do krypton, the last valence electrons would be 8. If we did xenon, it would be 8 valence electrons. Are you with me? So there's something special about these. And it seems like there's something special about the number 8. This is an exception. But what the point is this. Whenever an element or an atom has a filled valence shell, it becomes less reactive. Write that down. Whenever an atom has a filled valence shell, it becomes less reactive. Whenever an atom has a filled valence shell, it becomes less reactive. In fact, the noble gases are unreactive. They're so stable. They don't even react. Why are they stable? Why are they unreactive? Because they have filled their valence shell. Neon, maximum you can put on the second shell is 8. Neon has 8. Neon's done. It's not going to react with anything. Maximum you can have on the third shell is 8. Done. Argon has 8. Not going to react. Krypton has 8 valence electrons. Xenon has 8 valence electrons, so does radon. They don't react. They're chemically inert. Are you with me so far? Now helium doesn't have 8. It only has 2. So far so good? But that 2 is enough to fill the valence shell. So helium is non-reactive because its valence shell is full. That's the key. The filled valence shell is the key. Helium only has 2, and that's enough. The other ones all have 8. 8. Everyone say 8. 8. The octet rule. O-C-T-E-T. Write it down. O-C-T-E-T. Rule. Octet rule. The rule of 8. 8 valence electrons. The octet rule. All the atoms, well, all the representative elements, all the main group, want 8. 8. Except for hydrogen and helium. Hydrogen only wants 2. Why? Because if it has one more, it'll fill its valence shell, right? See that? They all want 8. And they'll all do extraordinary things to get to 8. They'll react with each other. They'll steal from one another. They'll try to steal from one another. They'll do all kinds of crazy and cool things to get there. 8. Unless you're helium, you're 2, right? All right. Now, nobody wants to do this. I don't want to write this out every time. It takes me a long time. It gets messy. It's hard to understand. So we came up with this much more elegant way of doing things called the electron dot symbol. Very, very nice way of looking at it. Because, here's the key, nobody cares about the electrons that are not valence. The valence electrons do all the work, the ones below it, no one cares. Now, let me say it a different way. They have to be there. But they don't do anything that's interesting to us. So we're going to ignore them. They accept that they're there. We don't want to talk about them. We want to talk about the valence electrons only. So we're going to use this thing called the dot symbol that represents how many valence electrons an element has. Let's talk about carbon. What group is carbon in? 14. How many valence electrons? 4. So carbon has 4 valence electrons, VE, valence electrons. So, remember, electrons repel each other, right? So they're going to fill themselves in around this carbon atom to maximize distance. They don't want to be too close to each other. So draw them like this. North, south, east, west. Gotta do them at all 4 corners. That way you maximize the distance. And those those dots, that's called a single electron. Single electron. Single and ready to mingle. That's important. Single and ready to mingle. Now, let's try another one. Let's try, well, one to the right. Nitrogen. How many valence electrons does nitrogen have? 5. Now, when you have 4 or less, you just stick them on there. 1, 2, 3, 4. North, south, and west. But now, nitrogen, north, south, east, and west. That's only 4, right? We have 5. After 4 is when you have to start doing something special. You start doubling them. Okay? So you have to make a pair. This is called a lone pair. And after 4 is when you start making them. So you could draw it like that. Or you can do this. Or, you get the idea, right? The lone pair can pretty much be anywhere around the nitrogen. It could be the third one, the fourth one too. Doesn't matter where you put it. I like putting them on the top. If I have, if nothing else matters, I put them up here. Sometimes I'll put them over here, depending. I don't care how you do it, as long as it's a lone pair and 3 single electrons. That's all I care about. Okay? How about, let's go over to the left of carbon. How about boron? How many valence electrons does boron have? Right. So now boron, you don't have to double anything. There's only 3, right? So I'll just put north, south, east. There you go, 3. 3 single electrons. Let's do something hard. Let's do fluorine. How many valence electrons on fluorine? 7. All right, here we go. North, south, east, west. How many's left? 3. Now you got to pair them, right? After 4, you have to start pairing them. So 1 here, 1 there, and how about 1 there? So now, lone pairs, single electron. 2, 4, 6, 7. Okay? Now I think everyone will agree, this is much nicer to look at than that. This is much nicer to look at than 2, 7. Right? This is better. Because it's quicker, shorter, makes everybody happier. Yeah, go ahead. Depends what I asked you. If I asked you for the electron dot symbol, you have to draw this. If I asked you for the arrangement, you draw this. If I asked you for both, you do both. Say that again? This one? No, it'll be 2, 7. Because nitrogen, fluorine has 9. Right, 7 plus 2. So if you ever get confused, just add them together. Right, good, very good. All right, how's that, guys? Good, right? No. All right, we'll take our break right here. And we'll come back in 10 minutes, okay? Yeah.
So on the test, you said you have multiple choice and
Yep.
with a response, right?
Yeah.
when you mean written response, you mean like we have to have an answer or just
Yep.
like solve it?
Well, if it's a conversion question, you show me all the work and
Well,
get to the answer. You know, if it's like this kind of stuff, if I say show me electron configuration of fluorine, you just draw
It's
it
not
out.
like definition, like oh, what is chemistry or?
Could be, but that's probably
Okay.
going to be in the multiple choice.
Okay.
Because that's just easier. Yeah, watch,
Okay.
watch the table.
Yeah.
Sure.
Anyone?
As long as they're taped up. Put it down. All right, guys, we're back. 10 minutes has come and gone rather quickly. All right, so we talked about valence electrons, how important 8 was, and about dot structures. Now, atomic size.
Write that down. Okay, atomic size. Now, atomic size is determined by this thing called the atomic radius. And the atomic radius, if you want to think about it, your atom was a circle. The radius is the distance from the neutrons, or pardon me, from the nucleus to the valence electron. That's called the atomic radius. Okay? Now, if you're a representative element, in other words, if you're not transition metals, your atomic radius will increase from top to bottom through a group. Your atomic radius will increase from top to bottom through a group. So, let's look over here. If we have an atom of lithium, lithium is smaller compared to francium. Francium is humongous compared to lithium. Okay? Increases down the group. So radius, atomic size, bigger as you go down. You just got a break. You're all awake now, right? One more time. Radius increases down the group. One more time. Radius increases down the group.
Yes.
I got 5 people of those. That's great. Now, it decreases within a period as you go from left to right. That's weird. Let's imagine you right here can be the nucleus and I will be the electron. If I'm lithium, I'm kind of hanging out right here. Radius, I don't know, 3 feet. Now, if I'm francium, I'm way over here. And now, imagine this is the beach. From the nucleus is the beach, electrons are you, enjoying the beach. If I'm lithium, there's only 2 people in front of me at the beach. So I can see the beach, I can smell the water, I can hear the sound, it's great. Not a lot of people around making that. And a highly attractive being, because this is comfortable, right? Now, francium, I'm a lot further away from the beach, right? I'm way back here. Way back here. And there's 86 people in front of me. Francium's 87, there's 86 people in front of me. This is not so good. It's crowded. People are laughing, frisbees are being thrown. People are generally having a good time and I'm miserable. It's a tough crowd, man. Really tough crowd. Anyway, so now, let me ask you a question. If you're francium, you're the valence electron on francium, the beach is way over there, all these people are here, how much energy is it going to take for you to leave this location and go home? Really? No. Not a lot. I'd get there in a minute. I wouldn't even stop the car. Right? Look at many people. You're far away from the beach. If you get to the beach and there's like 1 million people there, and you can't even see the ocean because there's so many people, you'd leave quick, wouldn't you? You wouldn't hang out. I mean, I wouldn't. But now, if you're lithium, there's nobody at the beach. Kind of 75 degrees, cool breeze blowing off water. You're going to be here for a while because it's really nice, right? You're taking a lot of energy to get you out of here, right? Okay. So the shorter the radius, the happier your electrons are. All right. Now I think it makes sense for everybody. As you go down a group, the radius gets bigger because you keep adding shells, you keep adding streets to your city, right? You keep moving further and further back. Now, as we go from left to right through a period, they get smaller. So as I go from here to here, lithium is actually bigger than fluorine. Fluorine is very small. Very small. So, in other words, fluorine, the valence electrons in fluorine, right here. And lithium, way out here. Right? Relative, it's all relative, right? So lithium's electrons are further away from the nucleus than fluorine's are. That doesn't make any sense, right? Because lithium has 1 valence electron, fluorine has 7, a lot more. So there's a lot more electrons trying to be in the same spot, right? Are you with me? that kind of flies in the face of what you believe, right? But, you know, the electrons are repelling you, you're all kind of being held tightly in one little area. Well, that tells us something very important about the nucleus. It's very attractive. Because fluorine has 9 protons, lithium only has 3. Are you with me? Fluorine's nucleus is 3 times more attractive than lithium. It has 3 times more protons, right? So the electrons actually get drawn in. Why? Because the protons are more attractive, because there's more of them. So they literally get drawn in. And their atomic radius is smaller because they're being drawn in. Are you with me? So fluorine is smaller than lithium. Size decreases through a period going left to right. Increases from right to left. Okay, so now, we all agree that lithium's valence electrons would be pretty hard to get to remove them. We all said francium, that electron would be hard pressed to stay, right? It's too far from the nucleus. So if that's true then, as we go left to right through the period, fluorine's electrons are close to the nucleus. It's small. So those electrons should be tightly held, right? If they're close to the bead, if you will. Are you with me? So fluorine's electrons should be tightly held. Take a lot of energy to get them to leave because they're so close to the attractive force. Does that make sense? So lithium, by comparison to fluorine, his valence electron should be easy to remove in comparison to fluorine, because they're further away. Are you with me? The closer your electrons are to the nucleus, the harder they are to remove, because they're made by the attractive force. Okay? Because that's important for the next thing we're going to learn. Next thing we're going to learn, ionization energy. Ionization energy. Energy required to remove an electron. The energy required to remove an electron. The energy required to remove an electron. And we just got through saying, the closer the electrons are to the proton, the harder they are to remove. Make sense? The further away the electrons are from the proton, the easier they are to remove. How's that? Well, that means in order, if we were to look at this group right here, lithium, sodium, potassium, rubidium. As we go down, they get what? Bigger or smaller? They get bigger. So the electrons are further away from the nucleus, right? Positive charge. So the ionization energy here should be what? Higher or lower than here? Should be lower here or higher? Should be higher, right? Because the electrons are closer to the nucleus. Here they're a lot further away. They're a lot easier to repel. Are you with me? Now, lithium compared to fluorine. Lithium is big, right? Compared to fluorine. As you go across the period, fluorine is smaller. The electrons are closer. So if the electrons are closer, it's hard to remove them, right? So the ionization energy for fluorine compared to lithium is higher, right? Because it's got more protons, the electrons are held closer, so they're harder to remove. Is that okay? That's ionization energy. So ionization energy will increase through a period and decrease down a curve. As you get bigger, your ionization energy decreases. As you get smaller, your ionization energy increases. That's how it works. Okay? Now, ions are a big deal. Ions are a big deal. We'll talk a lot more about them, I think it's in chapter 6. You guys all right with that? All right, now, let me pull up another set of slides here. Sorry. I didn't pull them up earlier. So if, one second, let me just get this down. Come on now. Here we go. All right. Someday today. Chapter 5. Sorry, bear with me. Here we go. All right. Now, before we get into chapter 5, let's just discuss a few more things real quick. If left to right to the theory, right? We transition ourselves from metals to metalloids to non-metals, okay? Non-metals have a high ionization energy. It's hard to take electrons from them. Metals, by comparison, have a low ionization energy. It's easy to take electrons from them. Are you with me? So, in general, metals will lose electrons in chemical reactions. Non-metals will actually gain them, will steal them. Okay? Now that's a topic for another day, but I want you to kind of start thinking about that. Metals have low ionization energy, they lose electrons. Non-metals have a high ionization energy. It's hard to take from them, but they're good at taking. They'll steal from everybody else. Okay? So that's chapter 6, keep that in mind. And we'll move into chapter 5, which is nuclear chemistry. It's kind of a little bit of a aside from the rest of the course, but we have to cover it. Nuclear chemistry. All right. Now, here is a symbology used commonly in chemistry and nuclear chemistry. Let's discuss. I-131 and 53. Now, here's how this symbology works. Whatever is written here, that is always a mass number. Whatever is written here is always an atomic number. Now, just to be clear, if I had something like this, C14, and I left that blank, there's nothing there. That's fine, not a big deal, right? Because you know the symbol is carbon, right? So all you got to do is look at the periodic table, and the periodic table will tell you the atomic number. Are you with me on that? Not every time you see this symbol when you see this written here. Sometimes it's left out. In fact, I'll just be honest with you, most times it's left out. Because the symbol is right here. Just look up on the periodic table if you don't know it. Make sense? Okay. So, this is carbon with a mass number of 14. Here's a little fun fact. Sometimes these things are written like this. Sometimes you'll see it written like this, where this is a mass number. This is quite common. This is quite common. This is not as common. But you sometimes will see it. This is not as common. Okay? So if I said C with a 14 superscript to the left, that's carbon 14. Carbon with a mass number of 14. This is also carbon with a mass number of 14. They're saying the same thing, just saying it differently. Is that okay with you guys? Pretty neat, huh? All right. Isotopes and radiation. Isotopes. Yeah. Weird. Well, now. Okay, well, let's start here. Wow. You all see that? I have a stroke right here. That was freaky. Thanks. Wow. Are you predicting something? Are all these salads I'm eating worthless? So this is hamburgers and fries? Is this going to happen anyway? Seriously, it's just going to happen anyway. I'm going to enjoy that. An unstable nucleus is radioactive. So nuclear chemistry occurs in the nucleus. It's an exception to everything else. All normal chemistry, which I mean non-nuclear, electrons do all the work. In nuclear chemistry, the nucleus does all the work. Okay? So it's kind of a tangent from normal chemistry. So, the nucleus becomes radioactive when it's unstable. It will emit small particles of energy called radiation. And that will make them supposedly more stable. Okay? Not always. Because remember, these things aren't thinking. They don't know if they do this, they'll be better. They just do it. And then they deal with the result. Now, we're going to deal with 4 types of radiation, but only 3 of them we're going to really dive into. Well, only 2 of them we're really going to dive into. The other 2 we're just going to talk about. There's alpha particles, there's beta particles, there's these things called positrons, and then there's this thing called gamma rays. Okay? So now, those are the 4 types of radiation we're going to talk about in class. So, let's talk about alpha. Alpha particles are sometimes abbreviated with the Greek letter alpha. And that is actually this. Helium, a mass number of 4. Helium with a mass number of 4. Now this has no electrons. So alpha particles are helium. They have a mass number of 4 and they have 2 protons, but they don't have any electrons. So it's what we call a cation. With the helium atom, that's devoid of electrons. And that comes from the nucleus of something. Okay? A nucleus is something that picks it up. Helium-42, alpha particle. It's very important that you notice it has a mass number of 4, right? So it has mass. So it occupies space. So it's a different type of matter. Beta particles. That is an electron. It's an electron. It has a mass number of 0 and an atomic number of -1. That'll become clear later on why it's -1. But for now, just accept its atomic number is -1. So I promise when we start working with it, it'll become clear why it's -1. But a beta particle is an electron with a -1 charge. Beta. Alpha particles, beta particles. Positron. I'm not even going to write it down. It's not that critical for this class. We don't talk too much about it. But you do have to know what it is. A positron is a beta particle with a plus charge. A beta particle with positive charge. Beta particle with a positive charge. And a beta particle is an electron, right? So a positron is an electron, but it's positive. That's weird. In other words, it's got the same mass as an electron, but it's positive. It has the same mass as an electron, but it's positive. That's pretty good, right? Form of antimatter. And it's used in PET scans, right? Positron, something topography. I don't know the East and gamma rays. Ooh, gamma. And sometimes you'll see it written like this. No mass and no atomic number. It's just energy. It's a form of energy. Type of energy. Okay? Alpha, beta, gamma. It's a type of energy. Pretty cool, huh? Pretty cool, huh? There we go. Well, if you don't know the answer, just lie. Yes, it's great. You're the best. Yeah.
So you said like when I'm saying nucleus is radioactive.
Yep. No, there's lots of things that go into what makes it radioactive. Way beyond the purview of this course. There's certain isotopes are unstable, so they'll emit things from the nucleus in order to try to achieve stability. Okay, so and it's hard to predict at this level, even at my level. I never really studied nuclear chemistry at a high level, so I don't even know how to predict it. So there's ways to predict it. Talking about nuclear physicists, they would tell you a lot more than I would about it. I will freely admit I'm not an expert in nuclear chemistry. Sorry. Organic chemistry, I'm all day long, but not nuclear. Sorry. A little shame. Radioisotopes, write that down. Now, radioisotopes. What's an isotope? No, not always. I think we should start there. I mean, this is important, but let's talk about isotopes first. Isotope equals question. What is an isotope? Close. Very good. Nicely done. Atoms of the same element. With different mass numbers. Atoms of the same element that have different mass numbers. So, if they're the same element, the protons must all be the same, right?
Yes.
Element, if it's carbon, all the atoms have 6 protons, right?
Yes.
Protons must be the same. If you want to say it like that. Neutrons vary. Neutrons can change. Let's say that one. Can change. The protons must be the same for all the atoms. If they're not, they're different atoms, right? But the neutrons can change. That's what makes an isotope an isotope. Are you with me? So I could have, and just look at this, I could have a carbon atom with six protons and 5 neutrons. 6 and 5 is 11, right? So that's mass number 11. I can have a carbon atom with 6 protons and 6 neutrons. Still carbon. Carbon mass number of 12. I can have carbon with 6 protons and 7 neutrons. Mass number of 13. They're all carbon. They just have different numbers of neutrons. Are you with me? And only one of those is radioactive. The other ones are stable. Is that okay? Now, let's talk about the most fun isotopes we have. Am I racist? Let's talk about hydrogen. Hydrogen exists as H1. It also exists naturally as H2. You can also find out there in the wilderness H3. You can find all 3. They're all hydrogen though, right? Everybody agree? So how many protons does each one have? How many? How many protons does each hydrogen atom in the world have? They all have 1. How do you know that? The atomic number. They each have 1 proton, right? Everybody okay with that? Everybody okay with that?
Yes.
How many electrons? 1. Because they're atoms, right? The protons and electrons have to be the same. Well, now you know I'm going to ask you about neutrons, right? Well, the mass number is number of protons plus the number of neutrons, right? So the number of neutrons is the mass number minus the number of protons. So, if we're dealing with hydrogen, and what number is this? What's this called? No. The mass number. Atomic number goes down here. It's written. These are mass numbers, right? So number 1 goes here, yes? Minus 1. So how many neutrons does H1 have? 0. I believe it's the only element we have that can have no neutrons. All the other ones, I believe, do have neutrons. Now, if you have H2, mass number is 2, right? So it's going to be 2 minus 1. So how many neutrons? What about H3? It'd be 3 minus 1, so 2. So these are isotopes of each other. Same atom with varying numbers of neutrons. Are you with me on that? Isn't that neat? H1 is not radioactive. H2 is not radioactive. H3 is radioactive. Okay? So not every isotope is radioactive. In fact, most of them are. Very few of them are, which is good. Now, why do I show this example? I give every class I teach, except for organic, because I can't fit it. Well, no, I actually do give it to organic, too. I tell every class this, because this is interesting. Because it's the only element, the only one, where the isotopes have unique names. No other atom does it. So, for example, carbon. Carbon 12, carbon 13, carbon 14, they're all called carbon. They don't change their names. They're just carbon. These all have different names, believe it or not. This one is called hydrogen. That's called hydrogen. This is not. This is deuterium. Even though it's still a hydrogen atom, it's called deuterium because it has a mass number of 2. This is called tritium. Or tritium. Okay, so they have different names. Now, they're all the same element. They're all hydrogen. But hydrogen with a mass number of 2, we call it deuterium. Hydrogen with a mass number of 3, we call it tritium. But they're all hydrogen. Okay? So now, I tell everyone this. Everyone I can think of. Because eventually, there's going to be a game show. Seriously. And it's going to be like, who wants to be a bazillionaire or something? And this is going to be one of the questions, I think. Because it's a hard question. The only element with named isotopes is hydrogen. Write that down. It's not going to be on your exam, but you never know in life. The only element with named isotopes is hydrogen. And if it's on Jeopardy, it's what is hydrogen? Thank you very much. I thought that was pretty funny too. You three are the only ones who even smile. The rest of people are like, yeah, forget chemistry, we want to go home. Well, I do too, damn it. But I'm working here. Now, here's the deal though. Here's the deal. I'm going to know you got the money. I'm going to watch it on YouTube, right? So I'm going to have my hand out for about 35%. I gave you a big question. If you win millions, I only want hundreds of thousands. No one's smiling now. Tough crowd. Usually everyone just agrees. Sure. All right, so make sure for an exam, if you can tell me, if I give you an isotope, you can tell me the protons, electrons, and the neutrons. Make sure you can do it, okay? It's not hard though, right? But just make sure you can do it. All right, now, some isotopes are radioactive. Not all of them. The radioactive ones are called radioisotopes because they're radioactive. They will undergo a change in the number of protons. They will undergo a change in the number of protons. Now that could convert it to a different element. The number of protons in fact changes. The element itself must change. Okay? Remember I said if carbon has 6 protons, it's carbon. If it magically gets 7, it's not carbon anymore. It's now nitrogen. No, tritium is still hydrogen because it has 1 proton. But we call it tritium because it has 2 neutrons. We're trying to differentiate those 3. And the reason for that is we use them a lot for special experiments. That's why we have different names for them. I believe that's one of the reasons why. The other ones don't have special names, so I know. All right. Isn't that neat? I mean, just saying tritium is kind of fun just to say it, isn't it? You ever heard of heavy water? Anyone ever heard of heavy water? Anybody heard of heavy water? Nobody? All right. Never mind. Never mind that. We'll move along. Oh, we went over all that already, believe it or not. Oh, there we go. Radiation protection. These things can be dangerous. These radioactive particles. They can be dangerous. In fact, all of them are dangerous. You have to protect yourself from them. You can't just willy-nilly jump around in radioactivity. It will make you sick. It will maybe kill you eventually. So, what do these things do? What do these radioactive things do? Well, they actually are dangerous because they can take electrons. Now remember, helium, alpha particles, don't have any electrons, right? They don't have any. So it's a +2 charge that's flying out there in the air somewhere. So imagine you're a helium atom with no electrons. You have 2 protons. You're attracted to other electrons, right? Are you with me? And let's just say your body is made up of molecules that have electrons in them, right? It's pretty easy, right? Your body has electrons, right? And they're doing something really good for you. They're holding you together, making your body work properly, yeah? So if a helium alpha particle comes into your body, it's got a +2 charge. If it collides with another molecule in your body, potentially it can take one of the electrons away. And that's bad. That's real bad. Because now you've taken a molecule that has an octet, remember that octet thing? And you've taken its octet away. So now that molecule is going to become more reactive to gain its octet back. Are you with me? And it doesn't care what it reacts with. So imagine you have something really reactive in your body that doesn't care what it reacts with. That's not a good situation to be in, because it might react with your DNA. That's real bad. Mutation, right? That could cause cancer. That's how these things can cause cancer, right? Beta particles. Well, they're electrons, right? So if a beta particle slams into one of your molecules that has a bunch of electrons, it might pick one out. And that's going to give you the same problem. You look so far. Gamma, even worse. It's a lot of energy. So with the energy, the electrons will absorb it and fly off, causing the same issue. You've all heard of free radicals, right? Ever watch any of that propaganda from Paul Wonderful? Antioxidants? No? They're kind of, antioxidants are huge, they're on the severe downside now. You've never heard of antioxidants? You have? One word. What's that? Oh no, you're supposed to drink them. Like tea and stuff is loaded with antioxidants. Phytochemicals they're called too. Yeah. They're supposed to be really good at cleansing your body of free radicals and this kind of stuff. Anyway, that's what they're talking about. Okay? So radiation can cause free radicals, but so can your normal metabolism. That's the way to go there. So you have to protect yourself from these nasty things. Okay? Now, beta's pretty big. I'm sorry, alpha. Alpha's pretty big. So all you got to do is, wear proper clothing. So wear, heavy shirt, lab coat, proper lab clothes, basically. If you're going to work with beta, you probably don't want to have bare arms with lab coat on or something with gloves on. If you're going to deal with beta, it's a little more serious. They say a lab coat and gloves, at least that's the minimum you should do. Now, the big one is gamma. That's the bad one. If you're going to work with gamma, you've got to get yourself behind lead and or concrete. Preferably both. Okay? Because gamma is very, very dangerous. It can go through the wall. It can go through you too, right? You've got to protect yourself from it. That's why if you're looking at X-rays and gamma rays are similar, they put this lead apron on you, right? And then the person doing it runs away. Seriously, right? It's kind of scary. And why are they doing that? Well, they're increasing their distance. That's what they're doing. They're increasing their distance from the source. Because the further away from the source you get, the better off you are. Okay? They're also limiting their time at the source. Okay? So that's what the person doing the X-rays is. Now that person doing the X-rays is probably doing 30 of those a day, right? So then you've got to get away from it. They can't be standing there for 30 X-rays a day because it's a cumulative effect. It'll build up over time. So get away from it, and they hide behind a wall and look through a little window, right? And then you know it's in your head, but all of a sudden your skin and your bones feel hot. No? What? The hull. I think about the Hulk. I guess I've never thought about the Hulk. I don't know. Is he even there? I don't.
He's supposed to get married, and now he can turn into like a goofy costume.
Oh, I didn't know that.
I never watched that.
No, I avoid superhero movies. I think Hollywood has gotten so reliant on nonsense like superhero movies that it's not even worth watching them because every week there's a new superhero movie out. And now Netflix has got 3 or 4 series of them, and Hulu's following them, and I'm like, come on, guys, think of an original story once. Just one original story. That's all I want to hear. Yeah, I know. That's why it's not original, because Marvel thought of it 30, 50 years ago. Seriously, they've been doing this for 50, 60 years, so they're just telling the same stories over again because there's no original thought anymore. Anyway, you got me on a tangent I shouldn't go down. I have a problem with movies. I really do. There hasn't been an original movie that I've seen in a while. The Conjuring was kind of unique. You know, people who've seen the movie know what I'm talking about. That was scary as hell. I loved it. That was great. Watch it sit in the theater, all of a sudden, I'm gonna go home. Time to go.
What about the Blair Witch Project?
That was pretty good. That was 20 years ago, though.
Yeah.
So don't forget that was 20 years ago. I know that we feel like it was only yesterday, but half the class doesn't even know what you're talking about. And Paranormal Activity was also pretty unique, but that was also 20 years ago. Well, maybe 15. What? Yeah, I like that term, based on actual events. Based on actual events. Well, there was a video camera in the movie. The video cameras are real, so it's based on actual events. You see what I'm saying? So, I thought it was good. It was entertaining. Anyway, we shouldn't go down these rabbit holes. I can talk about movies in Hollywood for a long time.
Circling in the Rainbow.
What?
Circling in the Rainbow.
I haven't seen that one.
You gotta watch it. Both.
Those books were written 20 years ago. Those books were written 20 to 30 years ago. Those stories are not. Those stories are not new. But that movie was done 20 years ago too. So it's a remake of a movie that was done 20 years ago from a book that was written 30 years ago. And I'm not saying Stephen King's not talented. He absolutely is. But these stories are not unique. They were told years ago. He knew. Anyway, you got me on the wrong path. I got to switch gears to come back. If I could talk for a long. I'm not gonna edit all this out now. He won the live stream. Don't tell Stephen King I said he was a talentless hack because I didn't say that. Just joking. I like Stephen King a lot. And he's from Maine, my part of the world. Nuclear reaction. See how this shifted gears back to the subject at hand? Nuclear reactions. All right. Let's do one. Let's do this one. So what we're going to do is we're going to start with this atom right here, this isotope, and we're going to break it down. We're going to emit helium, or alpha. We're going to emit alpha. Okay? So, Californium 251 is going to emit alpha. Now on an exam, I'm not going to tell you what alpha is. I'm just going to draw alpha. I'm just going to say that it's alpha. You have to know helium-42 is alpha. You have to know that for next week, okay? Plus, whatever that is. And that is what we're going to figure out. And it's easy. Trust me, this is easy. You're going to laugh when I tell you how easy this is. So we have Californium, CF. So if there's no atomic number printed here, you have to go to the periodic table. And unfortunately, no, it's right here. CF is right there. Californium, number 98, right? The atomic number of Californium is 98. So if it's not written on the exam, just look it up on the periodic table, it will be there. So that's 98. Now, these questions are so easy because I know every one of you in here can do basic arithmetic. I know you can. What number is 98 minus 2? 96. So this must be 96. Why? 96 plus 2 must equal 98. Whatever these numbers add up to must be that number. Are you with me? That's always true. Whatever number is here plus 4 must give me 251. Are you with me? What number must go here? 247, right? 247 plus 4 is 251. Must be that way. Absolutely must. So then, we need to know what the element is. We look up element 96. It comes in the periodic table, and it's almost hidden by the desk. This one right here. Cm. Curium. So, 247 plus 4, 251. 96 plus 2 is 98. Are you with me? So this must be correct because everything adds up. Double check that 96 is curium, and you must be correct. Everybody added up. Is that okay? Not bad, right? Right? It's pretty easy, right? All right, here's one for you. Sulfur, 32. It's going to lose alpha. So if sulfur 32 loses alpha, what will it make? One for you, yes. I'm sorry, what? What about what does it impact? The mass number? Oh, the number in blue, the 247, you simply subtract 4 from 251. And then at the bottom, 198, you subtract 2 from 98 and 96. Because the things on the right-hand side of the arrow, the numbers have to add up to the left side. Okay? So 96 plus 2 is 98. 247 plus 4 is 251. It has to be always going to be that way. Okay? Sulfur 32 becomes what if it loses alpha? I haven't done it yet. What is it? Yeah, you guys do it. Well, is everyone done? Does anyone want more time? I guess we're done. All right, what's the atomic number of sulfur? 16. What's the symbol for alpha? Okay. So then what must be the mass number? 28. So 28 and 4, 32. What must be the atomic number? 14 plus 2 is 16. So what is element 14? Silicon. Look at that. Now, don't be careful with these questions. They're worth like 5 or 10 points, and they're easy points if you don't make stupid mistakes, right? Double check everything, and make sure you get the right element here, okay? So, 1 second. 28 and 4, 32, that's good. 14 and 2, 16, that's good. Element 14 is indeed silicon, so that has to be right. Go ahead. Oh, you sure? All right, go ahead. Yeah, this is always off. So is that okay with you guys? Not hard, right? Not hard. So let's do beta. Again, not hard. The hard part of this actually is remembering what beta is. That's the hard part. Now, I just got through telling you that there are no electrons in the nucleus, right? And I also told you that beta particles are electrons, right? And I also told you nuclear chemistry has to do with things flying out of the nucleus, right? Not one of you said anything about the electrons flying out of the nucleus, right? But there is no electrons in the nucleus, right? There aren't any. There isn't any. No, there isn't. No, there's not. There's no electrons in it. Well, wait a minute. How does a nucleus throw out an electron if there aren't any to begin with? Aha! Great question, isn't it? Here's what happens. The neutron actually releases an electron. Don't worry what happens. It just releases it. Okay? But when it releases that electron, it becomes a proton. Well, it's really weird, isn't it? That's beta particle. Beta particle occurs when a neutron in the nucleus converts itself to an electron and a proton, and the electron is ejected. Okay? I know it hurts your head, right? Well, that's what it is. Now, I'm not going to even try to describe how this works. It's actually very complicated. But this is what beta particles are. A neutron converts itself to a proton and kicks out an electron. Okay? Now, that's all well and good. Let's do a problem. It's easy, trust me. C14 gives us beta plus whatever goes in here, okay? Now again, the hard part is remembering what is beta. What is beta? 0 and -1. Put an E there for electron, right? Okay, again, what's the atomic number of carbon? 6. So, something plus -1 is 6. What plus -1 is 6? 7. 7 plus -1 is 6. True? What plus 0 is 14? What is atomic number 7? Nitrogen. 7 plus -1 is indeed 6, right? Everybody? 14 plus 0 is, and 7 is nitrogen. See how easy that is? That's why, before when I said don't worry about why this is -1, just accept that it is, because you actually gain a proton when you do this, right? But it has to balance, right? So 7, 1, 6. Everyone okay with that? Let's do another one. I think I have one on here, actually. Yeah, cobalt 60. Write the nuclear equation for the beta decay of cobalt 60. Cobalt, for some reason I know, cobalt right there. Again, the hard part is remembering what beta is. Who's done? All right, you guys are great. What's the atomic number of cobalt? 27. What's beta? Green, is that showing up at all? You guys over there? You all see green? All right, what number must go here? 28. Plus -1 is 27, all right? What number goes here? What is element 28? 28 minus 1, 27. 60 plus 0, 50. Nickel is indeed 28. So that must be right. How easy is this? Easy, right? See? Exactly. There you go. That's the spirit. Gamma. Now, gamma we're not going to do anything with. I'm just going to show you what you need to look for. Okay? When? Oh. Wait. Harder questions. Okay. Whenever you have a gamma emitting isotope, the letter M will appear by the mass number. Okay? That letter M is just telling the user this is a gamma emitter, so be careful. And if you ever work with gamma emitters, it'll be slapped with a million labels to tell you it's dangerous. And it'll come in probably a big lead container, and it'll be really heavy. And well, it's one of those things, if you don't know what it is, don't touch it. So that's all it is. And then after the gamma emitter loses its gamma emitting ability, the element actually doesn't change. Just the M goes away. So the mass doesn't change, the protons don't change, it just gives off energy. Okay? I may draw this reaction like similar to this, that has an M, and say, what important aspect of this reaction do you know? You'd be like, oh, that's a gamma emitter, better be careful. I don't know, something like that. You put me on the spot, I can't word it that eloquently. All right. Forget transmutation. Radiation measurement. Radiation measurement. Commonly, radiation is measured with this device called a Geiger counter. It's written right here. A Geiger counter. Probably. Seems like all the cool toys are made by Germans. They're really big into chemistry. Geiger counter. Geiger counter. All right, let me just show you a quick Geiger counter. Looks like that. If you've all seen these in the movies, I know you have. Geiger counters detect beta and gamma, but they do not detect alpha. Yeah, it looks very. Yeah, the little ghost trap was very similar to that. Yeah. You say ghost? You mean the one from the '80s, right?
Yeah.
Okay, the Dan Aykroyd one. I haven't seen the new one yet. I want to wait for Netflix to get it or someone. I'd like to pay. All right, that's a Geiger counter. It measures beta and gamma radiation, not alpha. All right, and you've all seen it on the movies. It just kind of makes a clicking sound when it detects radiation. So it's really annoying audio, so you'll get away from the source. All right, here are some units for measuring radiation. Just write down what's in blue. Put down Curie, Becquerel, red, and gray. And we're not going to give you enough time to write the whole slide down because I want to move on from this. But write down what's in blue. And then go back in your textbook and the index, if these words up, write some definitions. Okay? I'm not going to wait for you guys to write all this crap down. A Curie and a Becquerel are both ways of measuring radioactivity. Okay, they're both ways of measuring disintegrations of atoms. Curie is used quite commonly in the United States. Becquerel is more common in Europe. But they're measuring similar things. They're not the same. They're not the same amounts, but they're both used to measure decay, radiation flying off. A rad, known as a radiation absorbed dose, that tells you about the amount of radiation absorbed by your body. So it kind of gives you an idea of how much you personally have absorbed. A gray does a similar thing. So rads and grays are similar but not the same. Okay? Becquerels and Curie are similar but not the same. So go ahead and write down what's in blue and look those up in your book. Write down your own definition for them. It's just a matter of memorizing them. There's no logic here. It's just what they're called. Everyone got the blue? All right. One more. REM. Write that down too. REM. Radiation equivalent in humans measures biological effects of different types of radiation. That's what REM is. Okay? So again, just write down REM, go to your book, find a definition, or go online or do whatever. It doesn't have to be your book, but just get a definition for them. Again, I'm not going to wait to write all that stuff down. Yeah, that's kind of boring, right? Exactly. See, no one wants to do that. REM, radiation equivalent in human. Okay, half-life. No math here either, just what half-life is. So let's go over this real quick. It's again, not hard. Not hard at all. Half-life of a radioisotope. Half-life of a radioisotope. Write the title down, please. Half-life. The definition is kind of in the name, right? The half-life. It's the amount of time it takes for half of something to go away. There's a better definition. Half-life of a radioisotope is the time for the radiation level to decrease by 1/2 of the original amount. Let's say you have 100 atoms, and all 100 are radioactive. And let's say you have a half-life of 7 days. So after 7 days, half of those atoms will be no longer radioactive. Then you only have 50 radioactive ones left. Okay? After another 7 days, you will have 25 atoms left. After the second half-life, these 50 atoms become 25. Follow this? After another half-life, you'll have 12.5. Well, 13, right? Rounded up, but you get the idea. Another half-life, and so on. 6.25, and so on. It'll just keep dropping by half. Does that make sense? Okay? That's half-life. So for every half-life a group of atoms go through, you keep losing half. Now, some isotopes have half-lives in the hours. Some of them have half-lives in the millenniums. Some of them have half-lives in the tens of millenniums. Some of them are just really stable. Okay? Now, a radioactive isotope that has a half-life in the hours has to be made when you need it. Does that make sense? Think about how many hours have been on the Earth right now. Anything that had a short half-life is already gone. Does that make sense? Anything with a long half-life is still around. Right? Some things have like half-lives in the tens of thousands of years, right? So those are probably still around. Most isotopes on our planet are not radioactive because the planet's been around long enough and these things have decayed, not radioactive anymore. But there's still radioactivity all around us, believe it or not. And our bodies, thankfully, have ways to defend against it. Kind of neat, huh? Here we go. We will finish today. Because I'm skipping over a lot of stuff. Ah, look at that. Fission and fusion. Again, definitions. You don't have to do any chemistry here. Definition. Nuclear fission and fusion. Just write that down, please. Nuclear fission and fusion. Fission and fusion. What does fusion mean? Just in general terms, what's the word fusion mean? To combine, to come together. Fission is the opposite of fusion. Fission means to break apart or to cut. Are you with me? So nuclear fission, nuclear fusion, nucleuses come together to make a new one. Nuclear fission, a nucleus breaks apart to make new ones. That's what they mean. In nuclear fission, a large nucleus is bombarded with a small particle, usually it's a neutron. What happens then is that large nucleus will split into smaller ones. So a big atom will split into two and give you two smaller atoms. Okay? And believe it or not, those two smaller atoms may also be radioactive. They may split apart. right? It's fat man and little boy. They're called. Originally, the weapons were called fat man and little boy. A little boy and fat man. No, fat man and little boy. Now, uranium-235 is usually where people think of this. This is what nuclear reactors use. Uranium-235 is not radioactive. Or no, it's slightly radioactive. It's slightly radioactive. When you put it together, you can make some uranium-236. So a nucleus has embedded itself, a neutron has embedded itself into the uranium nucleus, right? That nucleus will now split and form some other things. It doesn't matter what. The cool thing about this is once that nucleus, that large nucleus splits, it sends out 3 neutrons. It fires out 3 neutrons. It gives you a lot of energy, gives you a lot of heat. Okay? So because you get more neutrons, here's the reaction. So here's a uranium-235. Here's an incoming neutron. This neutron embeds itself in the nucleus. Okay? Makes this nucleus somewhat unstable, and then that nucleus will break apart. It'll fission. It'll form 2 other elements and give off 3 neutrons. So you put 1 neutron in, and you get 3 out. And you get a lot of heat. And that's not energy. Okay? So far, so good, right? Now, the fun thing is, those neutrons can go on and find other nuclei. So this neutron collides with this atom, splits it, you get 3 more neutrons, it finds 3 more atoms, splits them, now you've got 9, and they go on and they keep this reaction going. They keep propagating the reaction. And this is called a chain reaction. A chain reaction. When you put 1 in, you get many out. Okay? The reaction just keeps on going. It's self-perpetuating. It will keep itself going. Alright? Now, watch this. Every time this happens, you get heat. It literally gets hot. Okay? This is how power plants work. These power plants, I shouldn't say all power plants, most power plants rely on steam. You know that? Making steam. Steam turns a little turbine, or a big turbine actually, and that turning of the turbine makes electricity flow through wire. Which is how we get to watch TV. No fans of TV up there, okay. Okay, well this nuclear power plants rely on this reaction. This reaction causes heat. That heat is used to make steam. The steam is used to turn a turbine. The turbine powers our lives, our electrical lives anyway. So that's fission. Oh, fusion. Fusion, again, is the opposite of fission. Fusion is combining nuclei to make larger things. Now, the unfortunate part about fission is right now we need extremely high temperatures to achieve it. So we have to be really, really hot to get this to go. But what happens when you get it that hot is small nuclei will combine to make larger ones. The nuclei themselves, the protons, will just come together and form new elements. Now, the fun fact about fusion occurs continuously in the sun and stars, producing large amounts of energy. We all know how bloody hot it gets in the summertime. All that energy is coming from the sun, right? All that energy is coming from the fact the sun is a big ball of hydrogen, fusing the hydrogen together to make helium. That helium will go on and fuse again to make other elements, and fuse themselves together. Okay? And that's where all this heat comes from. All the energy that we get comes from the sun. It comes from this fusion reaction, fusing hydrogen atoms together to make helium. Isn't that wild? I want you to think about something over the weekend. Think about the food you eat. Whether you eat animal products or whether you don't eat animal products, it's all the same. All the energy we have, all the calories we eat, have come from the sun. The sun gives the energy to plants, so the plants can grow, right? We eat the plants. We feed the plants to our livestock. We eat the livestock, right? It all came from the sun at one point. Coal came from the sun. This vegetation has gotten old and became coal. Natural gas. Came from rotten vegetation, dead animals and stuff. Right? The sun. It was quite far back, but it came from the sun originally. Right? So imagine what would happen if that big, beautiful ball in the sky that we curse so often in the summer being too hot. Stop working. How long will it take for us to die? I don't know. Hopefully 30, 40, maybe 50 years. I'm looking at the long game here. What do you mean?
Like if the sun just like straight up like just disappeared without exploding.
I wouldn't think, wow, it would get really cold really fast. It would get really cold really fast. Good question. All right, guys, here, I don't know if you haven't picked up your quiz in a while. I got some quizzes here. Please come grab them. If you picked them up last week, it's probably good. Other than that, don't forget, exam next week, so be early. Folks that are sitting right here, please let me just connect my cables. I don't want anyone tripping. Yeah, what's the weather today? What table?
Wait.
Yep. Your table? Yeah. And I'll give you that, a formula sheet, and conversion factors. I'll give you a whole bunch of stuff. All right?
What's that website for the new?
Oh, I'll email it to you.
Okay.